the equation for a damped harmonic oscillator. Y double prime equals negative ky minus by prime. But in order for that thing to model a damped harmonic oscillator, B has to be greater than 0. Right? Because the negative sign, the sign in the equation makes it negative. And it needs to be negative because it is subtracting from the force. Okay, in the long run, all solutions to the damped harmonic oscillator equation, this guy up here, tend towards 0. And give an example of a damping force, friction. Yeah. There are others. Did anybody put something other than friction? Sure, air resistance. Okay, so today we're going to talk a little bit more about the damped harmonic oscillator. Remember that the model for the frictionless harmonic oscillator was y double prime is negative k over m times y. And m was the mass and k was the spring constant. Since the system was frictionless, the mass simply oscillates back and forth in perpetual motion. And when we guessed in some of our class activities, we guessed a solution to this model, and they were sine and cosine functions. So because this thing oscillates sinusoidally. But a damping force will slow the motion, right? To make the model more realistic, we can add a term that accounts for something that would slow the motion, friction, air resistance, something that dissipates energy from the system. So we're going to assume that the damping force is proportional to the velocity of the mass. Does that seem like a reasonable assumption? The faster it's moving, the more friction will be created. Or like with a falling body through the air, like the faster it's falling, the more air resistance there is. Right, so I think it's reasonable. So I'm going to adjust the differential equation to include a term that accounts for the damping force of friction. So a term that is proportional to velocity. Now, in terms of y, what represents velocity? Y prime, yeah, or dy dt, either one. Remember, velocity is the derivative of position. Okay. So my damping force has to be proportional to velocity. So it's going to be some constant b times y prime, my damping force. All right, so I'm going to start with the F equals mass times acceleration equation again. And we replaced acceleration with y double prime. And force, we just replaced last time with negative k times y. That's Hooke's law for springs. But now we also have to account for the fact that there is another force acting on that mass, and it's the friction, the damping force. So, and it is also negative because it is taking away from the energy of the system. Ooh, that's supposed to be a prime, minus by prime. So if I solve that equation for y double prime, just divide everything by m, and I'm going to have y double prime equals negative k over m times y minus b over m times y prime. Okay. So that is the harmonic oscillator with friction resistance. So we typically simplify it because k over m and b over m are just numbers. So we could sort of rename those p and q just to make it look cleaner. So y double prime plus py prime plus qy equals 0. Yep. Yes. Sorry, I should have include that negative. So if I were going to convert this to a second order differential equation, right, then, convert this second order to a system of first orders, then I start by letting y prime equal v. And then v prime is y double prime. So I just have to solve this thing for y double prime, and I would have negative py prime minus qy. So that's how you convert to a system. If you have a second order equation, generally let y prime equal v, and then v prime is y, whatever y double prime was. And now you have no more y double primes. All right, so I'd like to be able to study some solutions to this differential equation. So we're going to try to guess some. This is a theme that's going to keep recurring. We're going to get good at guessing solutions. So I'm just going to choose some arbitrary values for P and Q so we can have something more concrete to work with. So I just put in a 3 for P and a 2 for Q. Okay, so a solution to this differential equation is a function, y of t, who when you add up its second derivative, plus 3 times its first derivative, plus 2 times the function itself, you get 0. Meaning that y double prime, y prime, and y all have to be like terms. You have to be able to add them together to get 0. So what kind of function? E to the something, yeah. Yeah. If we have e to the something, its derivative, all of its first and second derivatives will all sort of look the same, so they'll be alike enough to add them. So we're going to guess that there's a solution of the form e to the st might exist. So I'm just going to write down my equation again, y double prime plus, what was it, 3? 3y prime plus 2y equals 0. All right, so if y equals e to the st, y prime would be se to the st, and y double prime s squared e to the st. So then I'm going to plug those guys into my equation and figure out what s will make this true, if there is an s that will make it true. This seems like a good guess, but if it's not a good guess, you would just plug it in. You go, oh, there is no s that would make it true. I got to guess again. Okay, so y double prime, s squared e to the st, plus 3 times y prime, which is s e to the st, plus 2 times y e to the st has to equal 0. So there's an e to the st in every term, so I can factor that out. And I'm left with s squared plus 3s plus 2. All right, so I've got two things multiplied together. The answer is 0. So the only way you can get 0 as a product is if one of the factors is 0. E to the st equals 0 when? Never. And then this quadratic, you could solve by factoring or the quadratic formula. It factors easily enough. So we get s is -1 and 2 and -2. So there we found two particular solutions. I've got y1 is going to be negative e to the negative t, and another particular solution is -2 e to the -2t. Sorry, it's just e to the -t and e to the -2t. I just replaced, in my guess formula, e to the st, I just replaced the s with the two values I just found, -1 and -2. So I actually just found two functions that make that differential equation true. So I haven't found the most general solution, but I have found two particular solutions. So this is the direction field for the system that I created using a computer. So I want to sketch the solution curves in the phase plane that corresponds to the two particular solutions we just discovered. So the phase plane is for the system, right? It has to be y and v, right? And that's why I had you convert this to a system earlier. Y prime equals v and v prime equals negative py prime minus qy. So I'm going to write that down. Y prime equals v and v prime is negative 3y minus 2y prime. Yeah. Nope. The prime goes on the one with the 3. Okay. So what's my initial condition? How am I going to sketch the solution that corresponds to e to the negative t, right? Where does it go in this phase plane? I need a point to start at so that I can follow the arrows. 0, 1. How do you know? Okay, so at time 0, you know what y is, right? But this doesn't have time in it, right? This is y on the horizontal axis and v on the vertical axis. So y of 0 we know. Yeah. Good. So let's see, if y1 we said is e to the negative t, then v1 will be what? y2 is e to the negative 2t, right? If y1 is e to the negative t, what's v1? No. Say it louder, Pat. Negative e to the negative t, because velocity is the derivative of position, right? So this is just negative e to the negative t. So my initial condition is when t is 0, right? So I need to know y1 of 0 and v1 of 0. Those will be the points that I plot in the phase plane. So y1 of 0 is 1, and v1 of 0 is negative 1. So I got to plot the point 1, negative 1. Let's look right here. And I follow the arrows, and it's just pointing me to the origin. So that's one of my solutions. And then my other solution is going to correspond to y2. y2 of t is e to the negative 2t, which means that v1 would be negative 2 e to the negative 2t. And then you plug 0 into both of those to get your initial point for the phase plane. Yes, thank you. And then v2 of 0 would be negative 2. So 1, negative 2 is another point. It's my other initial condition. And it also just points me directly to the origin. All right, so let's think about this phase plane a little bit. It looks like no matter where you start, so I'm going to put some other initial conditions on here. Like no matter what your initial conditions are, it looks like this thing sends you to the origin. Start over here, and it's going to sort of cycle down and send you to the origin. So yeah, the line v equals negative y. Yeah, that definitely seems like an important line in this picture. Yeah. Yeah. For some initial conditions, yeah. For some initial conditions, it will send you straight to the origin, like down here, right? It just goes straight in. But for a lot of initial conditions, it does seem like it sends you to that line first, and then you go into the origin. So does this make sense if that this would represent a harmonic oscillator that's damped with friction? It's like trying to cycle, right? That's why it does that thing where it sends it to the line. It's like trying to do something circular. It's trying to have a cyclical solution, but then it just sort of fades out, right? The motion, like it starts almost like it's gonna look like something oscillating, but then it just stops. Okay, you got some